Alrighty, so here we go. We're going to set up our second projectile motion problem example. This time, Joe is kicking a ball with an initial velocity of 20 meters per second at an angle of 37 degrees to the horizontal. We want to figure out what's the maximum height. We want to figure out what's the maximum height, how long the ball's going to be in the air, and how far the ball will travel along a level surface. Why can't I get this? There we go. 3 questions to solve. 1, 2, 3. Same process as always. You start by drawing a picture. Oh, here's the ball. It's going to get kicked. It's going to get kicked along a level surface. Sort of level. It is kicked with an initial speed 20 meters per second at an angle of 37 degrees to the horizontal. The ball is going to fly across the air. The ball's path is going to look something like this. It is a parabolic trajectory up and then down. Okay, pretty simple. Parabolic trajectory goes like that. How long will the ball be in the air? We want to know what's the maximum height. We want to know the time it takes to get to here. We want to know the range. This horizontal distance is called the range. All right. The same setup is true for all of these things. We want to set up DTV. We want to know DTV. We want to know over here DTV. For all those things. But in projectile motion, we have to separate our horizontal and vertical motions. So I make a little T chart here. What do I know in the X value? What do I know in the Y direction? Here, what do I know in the X direction? Here, what do I know in the Y direction? Here, X. That's supposed to be an X. And a Y. What do we know? So we'll call this position 0 for both. We'll call this time 0 for both. And the speed for the X, it's going to be 20 meters per second multiplied by the cosine 37 degrees. And the Y direction will be 20 meters per second times the sine 37 degrees. Sine 37 should be 0.6. So then sine 37 is 0.6. So this becomes 12 meters per second, and this is 16 meters per second. And the next thing that's really critical is that when we go from here to here, the acceleration in the X is nothing. If we're ignoring air resistance, there are no sideways forces, and the only forces acting on them are vertically. So the Y acceleration is negative 9.8 meters per second squared. And that'll be the same over here. There will be no acceleration in the X direction, but it will accelerate in the Y direction at negative 9.8 meters per second per second. Well, that's very helpful because that tells me that at least in the X direction, the speed doesn't change. We also know the speed at the top here in the Y direction, the maximum peak height has a vertical speed of 0. That's a critical bit of information. At the highest point, its vertical speed is 0. And I think that's all we know. But that's all we need to know. Now it's just see what we figure out. All right, so let's go to our problems. My first equation is always this one, VF equals VI plus AT. Well, in the X direction, the velocity is never changing, so that's easy. But let's look at this in the Y direction. Y direction. Well, from here to here, it starts at 12 and finishes at 0. So 0 equals that 12 meters per second plus negative 9.8 meters per second squared times time. We can now figure out the time it takes for it to reach its maximum height, which would be, bring this over here, minus 12 meters per second equals negative 9.8 meters per second squared multiplied by time. Divide both sides by negative 9.8. 12 divided by 9.8. Negatives will cancel out and we'll get 1.2 seconds. So the time to get to here is 1.2 seconds. And here's a key thing. It's the same time. Even though I did that in the Y direction, you get the same time. The time is the same for both. That's also important to recognize. It's the same time. Let's see, so 1.2 seconds there. Now we can do some other stuff. We can figure out how high it gets. We should be able to figure out this distance. Well, we can figure this in. Right, delta D equals VIT plus 1/2 AT squared. If we do this in the X direction, that goes away because there is no acceleration in the X direction. Delta dx equals VIT. That is going to be 16 meters per second multiplied by 1.2 seconds. 19.2 meters. How about in the Y direction? In the Y direction, delta dy equals VIT plus 1/2 AT squared. Delta dy, that's the maximum height. VIT, 12 meters per second multiplied by 1.2 seconds plus 1/2 negative 9.8 meters per second squared times 1.2 seconds squared. 1.2 squared gives us that times 9.8 times 0.5. This is going to be plus a negative 7.056 meters, and 12 times 1.2, 14.4 meters, plus negative 7.056. Delta dy, this is all dy, 7.34 meters. I've got too many significant numbers in there, so we'll just go to 7.3 meters. Right? We have 2 here, we have 2 there. So our answer should have 2. 7.3 meters. We just figured out the maximum height. Oops, wrong way. Make it smaller. Maximum height of the ball, 7.3 meters. How long will the ball be in the air? Well, you might recognize it. If the up trip and the down trip are symmetrical, if it takes 1.2 seconds to get to the peak, it's going to take 1.2 seconds to fall. So this is going to be 2.4 seconds. 2.4 seconds. 2.4 seconds. And now we want to know the distance in the X. This will have fallen another 7.3 meters. Gets back here to position 0. right? Change in position will be negative 7.3, or final position, the y dy equals 0. It gets back down to the ground. It loses that many meters. I don't know why I just added a 5 in there. It should have been 4. Whatever. And then this one, though. This is the one we need to know. Change in distance in the x equals initial velocity in the x multiplied by time plus 1/2 at squared. But again, in the x direction, that vanishes. So you get 16 meters per second multiplied by 2.4 meters. 38.4, and that makes all the sense in the world. It's just double 19 too. So how far will the travel on the world's surface? 38.4 meters. Got a couple of odds and ends here just to reiterate and make sure we're really clear on a couple of points. The sideways speed, it was going 16 here, it's going 16 here, it's going 16 here, it's going 16 here, 16 here, 16 here. The sideways speed never changes. Always 16 meters per second sideways, 16 meters per second sideways, 16 meters per second sideways. That never changes. However, that is not the case vertically. It started off going 12. My arrow's not to scale. Then at some point it was going 10. Then at some point it was going 8. Then at some point it's going even less, and it gets to 0 there. And then it starts going down a little bit faster, and it gains speed, going faster, and it gains speed again. And if it started with a speed of 20 meters per second in that direction here, it will finish, that's a terrible arrow, it will finish with a speed of 20 meters per second that way. This time it was 37 over on the left edge. It was at 37 degrees above the horizontal. Down here on the right, now it'll hit the ground at a speed of 20 meters per second at an angle of 37 degrees below the horizontal. Okay, and that is how to solve these problems. Make the picture, go along. Time is the same for both the x and the y coordinates, but that's about it. That's the same.